Wormholes capture the imagination as intriguing shortcuts through the cosmos, promising solutions for space travel, time travel, and even journeys to alternate universes. Their allure is not just in their science fiction appeal, but in the real scientific theories and predictions that have shaped our understanding of these fascinating structures over time. The idea of wormholes began with Ludwig Flamm in 1916, when physicists were grappling with the complexities of Einstein's field equations in general relativity. Flamm was exploring solutions and proposed the existence of white holes, which would be the opposite of black holes. In his theory, matter falling into a black hole could be expelled through a white hole, connected by a kind of space-time conduit. This conduit, or tunnel, would bridge 2 points in space-time, potentially even in different universes. Though his ideas were speculative and not widely recognized at the time, they laid the groundwork for future developments. The concept gained traction when Albert Einstein and Nathan Rosen revisited it in 1935. Their paper extended Flamm's idea, introducing what we now call Einstein-Rosen bridges. These bridges, which are a type of wormhole, were initially proposed as shortcuts between distant points in space-time within the same universe. This conceptual leap highlighted the potential for wormholes to act as cosmic shortcuts, allowing for rapid travel between distant locations. To visualize how a wormhole might work, think of a flat sheet of paper representing the universe. If you draw a point at each end of the paper and then fold the paper so that the 2 points touch, you've created a shortcut between them. If you then poke a pencil through the folded paper, that pencil represents the wormhole, a direct connection between 2 points that bypasses the distance of the flat paper. This analogy helps illustrate the basic idea. A wormhole is a tunnel-like structure that provides a shortcut through space-time. However, while the mathematics behind wormholes suggests they could exist, their practical discovery and utilization are far from guaranteed. Theoretical models show that wormholes might be possible, but they also come with significant challenges. One major issue is their stability. Theoretical work indicates that if a wormhole were to form, it might be incredibly unstable, collapsing almost instantly due to gravitational forces. This collapse would happen so quickly that not even light could pass through, making them practically unusable for any form of travel. The idea of wormholes remains compelling largely because they offer a solution to some of the most pressing problems in physics. They provide a theoretical means of overcoming the vast distances between stars and even offer tantalizing possibilities for time travel. Yet, despite the elegant solutions wormholes offer, the reality of their existence and stability is still uncertain. The fascination with wormholes persists because they sit at the intersection of profound theoretical physics and imaginative science fiction, pushing the boundaries of what we know about the universe and our place within it. Reversible wormholes, the kind of wormholes that could theoretically allow matter to pass through, involve a fascinating mix of theoretical concepts and daunting challenges. At the heart of the discussion is the need for exotic matter, a hypothetical substance with properties that defy our conventional understanding of physics. Exotic matter is proposed to possess negative energy density, an essential feature for keeping a wormhole open. In simple terms, this means it would exert repulsive gravitational forces, counteracting the intense pressure that would otherwise cause the wormhole to collapse. Negative mass, a form of exotic matter, would behave counterintuitively to positive mass. Instead of being attracted by gravity, it would be repelled, allowing the wormhole to remain stable. This counteracting force is critical, as without it, the wormhole would quickly pinch off, rendering it useless for practical purposes. However, the search for and use of exotic matter presents its own set of problems. Negative mass, if it exists, is currently undetectable with our present technology, and no examples of exotic matter have been observed. Even if such matter could be found, integrating it into a wormhole and maintaining its stability would be extraordinarily complex. The introduction of ordinary matter, such as a person or spacecraft, could disrupt the delicate balance required to keep the wormhole open, potentially leading to its collapse. Another significant challenge is Hawking radiation, a theoretical prediction that black holes emit radiation due to quantum effects near their event horizons. Similar effects are thought to apply to wormholes. This radiation could cause the wormhole to shrink and close, limiting its usefulness. The presence of Hawking radiation would impose a strict time limit on how long a wormhole could remain open and stable, complicating any plans for using them for space travel or communication. Alternative theories offer intriguing possibilities for wormholes, though they also come with their own complexities. The E=ER conjecture, proposed by Leonard Susskind and Juan Maldacena, suggests that quantum entangled particles are connected by wormholes. This idea attempts to bridge the gap between general relativity and quantum mechanics, offering a potential avenue for unifying these two fundamental theories. If correct, this conjecture could offer a new perspective on how wormholes function at a quantum level, though it remains a theoretical proposal rather than a practical solution. String theory provides another intriguing framework. According to some interpretations of string theory, wormholes could have been created during the early moments of the universe. These primordial wormholes might have been tiny, on the Planck scale, but cosmic inflation could have expanded them to a macroscopic size. If such wormholes exist and can be stabilized, they could offer a means of creating shortcuts across the universe. When it comes to practical uses, wormholes could revolutionize space travel. If we could create a network of wormholes, it might be possible to establish a wormhole commuter hub, allowing for rapid travel across vast distances in space. This would transform our approach to exploring and inhabiting other parts of the galaxy. Additionally, wormholes might enable time travel, a concept that has fascinated both scientists and science fiction enthusiasts. By accelerating one end of a wormhole to near the speed of light, time dilation could create a scenario where traveling through the wormhole allows movement backward or forward in time. However, practical time travel via wormholes faces significant limitations and paradoxes. The process of time travel would not allow for free movement to any time or place. Instead, you could only travel to moments before or after the creation of the wormhole itself. For instance, you couldn't travel back to prevent historical events like the assassination of historical figures. You'd be limited to arriving at times when the wormhole was operational and at the location where the other end of the wormhole was positioned. The future of wormholes remains a tantalizing frontier in both theoretical and experimental physics. Recent developments have sparked significant excitement and speculation, particularly around advancements in technology and understanding that could bring us closer to unraveling the mysteries of these cosmic shortcuts. In 2022, news stories emerged claiming that scientists had created the first ever wormhole in a lab. However, these reports were met with skepticism and confusion. The excitement stemmed from a paper published by a team led by Jane Ferris, which explored the ER=EPR conjecture using quantum computers. The conjecture, proposed by physicists Leonard Susskind and Juan Maldacena, suggests that wormholes, ER, might be linked to quantum entanglement, EPR. While the research used simulations to test these ideas, the actual creation of wormholes remained speculative. The media's sensationalism around the paper led to misinterpretations, suggesting breakthroughs that were not yet realized. Despite the sensational headlines, the work done with quantum computers represents a meaningful step forward in our understanding. By testing theoretical models like the ER=EPR conjecture, researchers are inching closer to reconciling general relativity with quantum mechanics. Such advances could eventually lead to real discoveries about wormholes, though we're still far from practical applications. Theoretical physics continues to explore new possibilities, and one intriguing theory suggests that wormholes might be optical illusions. This idea relies on the concept that wormholes, if they exist, might require additional spatial dimensions. One analogy often used is the Klein bottle, a four-dimensional mathematical construct that appears to have a single side and no boundaries in its higher dimensional form. In 3 dimensions, a Klein bottle looks like it has an opening, but this is merely a shadow of its true form. Similarly, the entrances to wormholes might be illusions created by higher dimensional spaces, making it seem as though there's a tunnel, when in reality, there might not be one. As we continue to investigate these possibilities, the future of wormholes remains a blend of hope and uncertainty. While we await further discoveries, the excitement about potential breakthroughs in space and time travel fuels our imagination. Each advancement in theoretical and experimental physics brings us one step closer to understanding whether wormholes are more than just theoretical constructs. For now, the journey toward uncovering the true nature of wormholes is ongoing, keeping us on the edge of our seats as we explore the limits of our universe. Well, that was it for today. Don't forget to subscribe to the channel, and if you want to know more about the gateways to space, watch our video on everything about the Dyson Sphere in 10 minutes. See you again. Bye.